Edexcel Decision 1, Linear Programming 4, Adapted Simplex Methods, Minimization Problems. So here we have a linear programming problem with two decision variables x and y, and this time the objective function is to minimize. So we want to minimize p equals 4x minus y, subject to the two constraints seen here, with obviously trivial constraints of x is greater than or equal to 0 and y is greater than or equal to 0. So as we can see in this diagram, we know that the optimal solution is at one of these four vertices, and this line in green is the objective line. We can see that as x gets smaller and y gets bigger, p decreases. And actually, if we tested all these vertices or used our objective line, we would find that this vertex here is the optimal vertex that gives us the minimum value of p, and this value would be -2. This is obviously an easy problem to do graphically as it's two-dimensional, but if we had 3 or more variables it'd be rather difficult to do, so we need to look at how we use the simplex algorithm. The simplex method maximizes the objective function, so we need to change this problem into a maximum problem. And we do this by writing the objective function, which can be seen here, as q equals minus p, which means that q is in fact minus 4x plus y. So we now want to maximize q, which equals minus 4x plus y, subject to the constraints 3x plus 4y plus s1 equals 12 and 2x plus 5y plus s2 equals 10. So we have introduced two slack variables. So therefore we must introduce the trivial constraint s1 is greater than or equal to 0 and s2 is greater than or equal to 0. So remember that the simplex method starts at the vertex 0, 0, and in order for the simplex algorithm to work, 0, 0 must be a feasible solution to the problem. Since 0, 0 is a feasible solution, it's fine to use the simplex algorithm. And in order to use the simplex algorithm, we must rewrite the objective function as q plus 4x minus y equals 0. And now we're ready to start. So here's the simplex tableau. We need to fill in this table, and we do so by including the objective function on the bottom row. So we're going to fill that in first. So we know that our coefficients are 4, minus 1, 0, 0, and the right hand side is 0, and we know that our basic variable at this stage is q. Now have a go at filling in the other two rows. And here we have our initial tableau, and we are ready to start the algorithm. So don't forget that the basic variables are those that are non-zero at any stage in the algorithm, and the method starts at the origin, so at this time x and y are equal 0, and therefore the slack variables are non-zero. So now we need to perform our first iteration. So the first thing we need to do is identify the pivot element. You can see that the most negative element in the objective row is -1 and it's in column Y, so this is our pivot column. And then we perform our ratio test. Two is the smallest positive value, so S2 is our pivot row and 5 is our pivot element. So now we need to reduce this pivot element to 1. So we divide row 2 by 5 and we get 0.4, 1, 0, 0.2 and 2. And our basic variable now becomes Y. So we look at row 1 and we need to reduce the element in the Y column to 0. So we take row 1 and we subtract 4 lots of the new row 2 from it. And we get 1.4, 0, 1, negative 0.8 and 4, with our basic variable still being S1. And then for row 3, we perform the operation row 3, add the new row 2, and we get 4.4, 0, 0, 0.2 and 2, and the basic variable stays as Q. So since there are no negative elements in the objective row, we don't need to perform another iteration and the problem has been solved. So this is a solution to our problem, and now we just need to interpret the table. So our basic variables are found by identifying columns that have 1 in it and lots of zeros. So here we can see our basic variables Y and S1. So our non-basic variables are X, which must equal 0, and S2, which also must equal 0. So this means that Y is 2, according to our table, and S1 is 4. So this refers to the solution being at the coordinate 0, 2, which is up here, and Q equals to 2, as can also be seen in the table. To maximize Q but minimize P, this means that P is negative 2, as we defined Q to be negative P. So our next session is on problems involving greater than or equal to constraints.